One of the most amazing facts in physics is this. Everything in the universe, from light to electrons to atoms, behaves like both a particle and a wave at the same time. All of the other weird stuff you might have heard about quantum physics, Schrodinger's cat, God playing dice, spooky action at a distance, all of it follows directly from the fact that everything has both particle and wave nature. This might sound crazy. If you look around, you'll see waves in water and particles of rock, and they're nothing alike. So why would you think to combine them? Physicists didn't just decide to mash these things together out of nowhere. Rather, they were led to the dual nature of the universe through a process of small steps, fitting together lots of bits of evidence, like pieces in a puzzle. The first person to seriously suggest the dual nature of light was Albert Einstein in 1905. But he was picking up an earlier idea from Max Planck. Planck explained the colors of light emitted by hot objects, like the filament in a light bulb. But to do it, he needed a desperate trick. He said the object was made up of oscillators that could only emit light in discrete chunks, units of energy that depend on the frequency of the light. Planck was never really happy with this, but Einstein picked it up and ran with it. He applied Planck's idea to light itself, saying that light, which everybody knew was a wave, is really a stream of photons, each with a discrete amount of energy. Einstein himself called this the only truly revolutionary thing he did, but it explains the way light shining on a metal surface knocks loose electrons. Even people who hated the idea had to agree that it works brilliantly. The next puzzle piece came from Ernest Rutherford in England. In 1909, Ernest Marsden and Hans Geiger, working for Rutherford, shot alpha particles at gold atoms and were stunned to find that some bounced straight backwards. This showed that most of the mass of the atom is concentrated in a tiny nucleus. The cartoon atom you learn in grade school, with electrons orbiting like a miniature solar system, that's Rutherford's. There's one little problem with Rutherford's atom. It can't work. Classical physics tells us that an electron whipping around in a circle emits light, and we use this all the time to generate radio waves and X-rays. Rutherford's atom should spray X-rays in all directions for a brief instant, before the electron spirals in to crash into the nucleus. But Niels Bohr, a Danish theoretical physicist working with Rutherford, pointed out that atoms obviously exist, so maybe the rules of physics needed to change. Bohr proposed that an electron in certain special orbits doesn't emit any light at all. Atoms absorb and emit light only when electrons change orbits, and the frequency of the light depends on the energy difference in just the way Planck and Einstein introduced. Bohr's atom fixes Rutherford's problem and explains why atoms emit only very specific colors of light. Each element has its own special orbits, and thus its own unique set of frequencies. The Bohr model has one tiny problem. There's no reason for those orbits to be special. But Louis de Broglie, a French PhD student, brought everything full circle. He pointed out that if light, which everyone knew is a wave, behaves like a particle, maybe the electron, which everyone knew is a particle, behaves like a wave. And if electrons are waves, it's easy to explain Bohr's rule for picking out the special orbits. Once you have the idea that electrons behave like waves, you can go look for it. And within a few years, scientists in the US and UK had observed wave behavior from electrons. These days, we have a wonderfully clear demonstration of this, shooting single electrons at a barrier with slits cut in it. Each electron is detected at a specific place at a specific time, like a particle. But when you repeat the experiment many times, all the individual electrons trace out a pattern of stripes, characteristic of wave behavior. The idea that particles behave like waves and vice versa is one of the strangest and most powerful in physics. Richard Feynman famously said that this illustrates the central mystery of quantum mechanics. Everything else follows from this, like pieces of a puzzle falling into place.